Okay. Suppose there's a triangular frame. It's an equilateral triangle of side A. And let's say there is a uniform magnetic field directed into the plane of your screen. Right. Magnetic field is uniform, as I said. And assume this triangular frame is moved to the right with a speed v. Okay, it's a conducting frame. So one of you tell me what happens inside this triangular frame. Due to the magnetic field, or when it is moved in the magnetic field, what happens inside the frame? Like, think from the fundamentals. It's a conductor moving inside a magnetic field. Just yesterday we talked about, in the last class we talked about what happens when conductor moves in a magnetic field. So think in those terms.
Sir, EMF will be generated.
EMF will be generated. How? Like what
When it's
exactly?
moving, sir.
What actually happens when a conductor moves in a magnetic field? Like what gives rise to the EMF? Okay, keep this point in mind, all of you. You need to know the basics. Okay? Like, if you see any new situation, no, you can only answer it if you know from the fundamentals, basically what happens, how a formula is derived and all. Conductor, any object, whether it's a conductor or insulator, whatever, it has protons, electrons in it. Conductor has something called free electrons. Okay. Now, when this conductor is moved inside the magnetic field, the charges inside it, protons as well as electrons, experience force due to the magnetic field. Okay. Force due to magnetic field on any charge is given by Q V cross B, right? So if charge is positive, force will be in the same direction as V cross B. If charge is negative, force will be opposite to V cross B. Now you look at the direction of velocity and magnetic field and tell me, one of you, what is the direction of V cross B in this situation? What is the direction of V cross B? V is to the right, magnetic field is into your screen. So what is the direction of V cross B? Isha, can you tell?
Sir, upwards.
Upwards, correct. Okay. And as we just discussed, positive charges experience force in the same direction as V cross B. So effectively what will happen? The positive charges of this ring, okay, some positive charges in this ring, they get deposited here. Okay. Actually, positive charges, that is protons, are inside the nucleus. They don't move. Fine. Actually, what happens is electrons go away from there. So automatically some positive charge will be left. So that is what happens. And V cross B is upward. Positive charge experiences force in that direction. Negative charge experiences force in the opposite direction. As a result, the conduction electrons that are there, they will come down like this. Okay, you will see a charge separation happening. So let me indicate it here. On positive charges, the force is in the upward direction, and on negative charges, the force will be in the downward direction. So this is what is going to happen. So when I first asked you what happens inside the conductor when it moves inside the magnetic field, you should have said charge separation happens. Okay. Now someone said there will be EMF induced. Rishi, can you tell me Faraday's law? When will there be EMF induced in a loop or a coil? According to Faraday's law, or from what Faraday observed, when is EMF induced in a coil?
Sir, when there's electromagnetic induction,
How does that happen?
uh,
Anyone? Sashank, Isha? Okay. When magnetic flux through a loop changes, there will be EMF induced in it. Now, this is a triangular loop, that's fine. There is magnetic field into the screen. So there is some flux through this triangle. But the triangle is completely inside the magnetic field. When you move it also, it continues to stay inside that magnetic field. So you all tell me, is flux through this triangle changing at the moment? If you think it is changing, tell me why it is changing. Is the area changing? Is the magnetic field varying? Or is the angle between them changing? Why do you think flux will vary? That also you have to tell. Otherwise, you tell flux is not varying. What do
sir,
you
I
think?
don't think it's varying.
It will not be varying. Okay. See, there are some field lines passing through this triangle. When you move it to the side also, to the next position, the area didn't change. The magnetic field didn't change. The orientation between the loop and the magnetic field didn't change. Why will the flux change? Okay. If it goes out of the magnetic field, then flux can change. But here it's completely inside the magnetic field and it continues to be inside the magnetic field. So no change in flux. No change in flux here. Magnetic flux. That means there is no EMF induced in the loop. Okay, understand this situation carefully. Wantedly, I took up this situation. Total EMF induced in the loop is 0. But is there any potential difference between points of the loop? Yes, it is there. Okay, you consider this topmost point, call it as A, and you consider this bottommost point, call it as B. Positive charges went to A and negative charges came to B. So there is a potential difference between A and B. Okay, if I ask you how much is the potential difference, you can tell that also. Yesterday we derived one formula for motional EMF, BVL or B dot V cross L. In this case, magnetic field is in the Z direction. Fine. Velocity is in the X direction. Fine. If you want potential difference between A and B, you will have to take the length in the Y direction. Means you have to take this length. That's all. And for an equilateral triangle, this length is A root 3 by 2. You can take that as L, perpendicular length. Then there will be a potential difference between A and B. And how much will that be? Magnetic field, speed, and perpendicular length. So it becomes BV A root 3 by 2. That much potential difference is there between A and B. Okay. Does that mean Faraday's law is valid, invalid? There is an EMF generated. Faraday said if flux doesn't change, EMF should not be generated. Does that mean Faraday's law is violated here? No. There is a potential difference between the 2 points. That's fine. Now you go from, imagine moving from B to A. If you move from B to A, the potential difference, I should say potential, the potential increases by this much, BV A root 3 by 2. Again, if you come back from A to B, the potential falls by the same amount. So the total EMF in the loop is 0. Okay, so what Faraday said is correct. Flux is not changing, EMF is not induced. Okay, net EMF induced in this loop is 0. Does that mean there's no potential difference between any 2 points? It is there. Okay. So effectively, this situation is like this. Let me explain. We got the potential difference between A and B, no? A is the topmost point, B is the bottommost point. Between them, the potential difference is this much. Let's call it delta V. Now, you know that A is positively charged. That end got positive charges and this side got negative charges. So effectively what happens is, as you go from B to A, the potential increases. So you can imagine something like like a cell between A and B whose EMF is BVA root 3 by 2. That much potential difference. Again, from the other side, when you come back from A to B, the same potential will decrease now. A is positive side, B is negative side. So effectively, it's like this. Here also the EMF is BV A root 3 by 2. So from between B and A, there is a potential difference. But in the loop as a whole, if you see, the EMF is 0. That is what happens. Yeah, Rishi, you raised hand, you can ask.
So in all cases, when there's no change in flux, there will be no EMF, right? Like in all cases.
If magnetic flux does not change, there won't be induced EMF.
Okay, sir.
Okay. Here also, the entire triangle, if you see as a loop, the EMF is 0. But does that mean there is no potential difference between any 2 points? It is there. There is potential difference.
So if any one of them is there, we have to calculate it, right?
What do you mean any one of them is there?
Like if there's either a potential difference or like if there's or if there's flux.
See, if conductor moves in a magnetic field, charge separation will occur. So there will be potential difference between some points. Okay, so that will always be there if conductor moves in a magnetic field.
Oh, okay, sir.
But for the loop as a whole, if you see, since this loop is entirely inside the magnetic field and it stays inside the magnetic field, the flux is not changing. So for the loop as a whole, the EMF is 0. So within the loop, the EMF, the voltage increases and falls also as you move from point to point or as you move along the loop.
Okay, sir. Okay, understood.
Okay, Shashank is saying, sir, if this coil were to be rotating, would there be a change in flux at any point? Definitely. See, if coil rotates in a magnetic field, no, the angle between the area vector and the magnetic field vector keeps changing. And if angle changes, the flux changes. Okay, we'll discuss those situations also. That will also come under motional EMF itself. Okay. So you can look at this question like this also. Directly, they can give you something like this and ask what is the potential difference between A and B. Okay. To find out potential difference, don't blindly apply Faraday's law. That is what you need to learn from this. Faraday's law gives you the total EMF of the loop. It can't give you potential difference between two individual points of the loop. Okay, so according to Faraday's law, the total EMF in this loop is 0, and we have also shown that it will be 0. But between two particular points, if you are asked potential difference, imagine a line joining those 2 points first. Get the length of that line. In this case, it becomes A root 3 by 2, the height of the equilateral triangle. Then you use the formula for motional EMF, which is B into V perpendicular into L perpendicular. Here in this question, luckily, magnetic field was in Z direction, velocity was in X direction. So velocity was already perpendicular to magnetic field. No need to take the components. And because magnetic field is in Z direction, velocity is in X direction, the length must be taken in Y direction. And A and B lie along the Y-axis itself. So you could use that length directly. So that way you can tell the potential difference. Okay. In this same question, suppose you are asked potential difference between A and let's say this point C. Between A and C, if you are asked, you look at the length vector between A and C, it's like this. Okay, that is the side of the triangle, that's fine. But tell me, is this perpendicular to both magnetic field and velocity? The
No,
line
sir.
connecting C and A, is it perpendicular to both the magnetic field and velocity? It is not. So what you need to do is you need to take its component in the perpendicular direction, which again becomes the same A root 3 by 2, height of the equilateral triangle. If you take the component of the side in the vertical direction, it becomes the height of the equilateral triangle. So between A and C also, the potential difference is the same as between A and B. That is what this shows. Okay. In fact, this entire base will be at one potential. This upper vertex is at another potential. Okay. You can look at it this way also. Consider the points B and C. Between B and C, if you imagine a length vector, it will be like this. The length vector between B and C, we know it is half the side of the triangle. It will be like this. Now see, magnetic field is in Z direction, velocity in X direction. This length is also in X direction. Does it have any Y component? It does not. The line connecting B and C cannot have a Y component because it's along the X axis. And because it cannot have a Y component, you can say the potential difference along this line is 0. That means potential at B is same as potential at C. Okay, that entire base will be at the same potential. Okay, I'll give you one more question like this. Similar situation, imagine there is a uniform magnetic field directed into the plane of the screen. And assume there is a conducting ring like this. Okay. Magnetic field, take it as B. This conducting ring is moving to the right. Okay, it is well inside the magnetic field. It's not going out of it. It is moving to the right with a velocity V. Assume its radius is R. Okay, I'll mark 4 points on this ring. So what is the EMF induced in the ring as a whole? How much is it? Next, potential difference between A and C. Next, potential difference between B and D. Next, potential difference between A and D. Okay. Try this, all of you. Any answer? Total EMF in the ring? Okay, Shashank, do you think flux through this ring is changing as it moves inside this magnetic field?
No.
No. Then what will be the total EMF induced in it?
Zero.
Zero. Answer to the first part is zero. Okay, the ring is completely inside the magnetic field. So the area through which the field lines pass is not changing. The field strength is not changing. And the orientation is also not changing. So the flux through this ring does not change. Induced EMF totally will be zero. Correct. Now potential difference between A and C. One of you tell me, should there be a potential difference, any potential difference between A and C, and why? Will there be potential difference between these 2 points and why? Isha, what do you think? Anyone? It's a conducting ring moving inside a magnetic field. When conductor moves inside a magnetic field, what happens? Or what does the magnetic field do to the charges inside the conductor? What happened? You all are busy with something else or what? Rishi, what do you say? What does the magnetic field do to the charges in the conductor?
Sir, will there be a force acting on it?
Why not? Okay. Charge moving in
Yeah.
a magnetic field will experience a force. Which way will the positive charges go and which way will the negative charges go?
Sir, the force will be perpendicular to it. So, uh, the positive, I'm not sure about this, sir.
Tell me the formula for magnetic force on a charge.
Uh,
When a charge Q moves inside a magnetic field, what force does it experience or how much force does it experience?
so QV into B.
Don't say
Is
into.
that right?
Q V cross P. Correct. That's the magnetic force acting on a charge when it moves inside a magnetic field. Now, positive charges, if Q is positive, then force and V cross B will be in the same direction. So force is along the cross product V cross B. If the charge is negative, it means there is a negative coefficient between force and V cross B. So force will be opposite to V cross B on negative charges. Now in this case, V is to the right, magnetic field is inward, so V cross B is upward. It's the same case that we have taken many times. If V cross B is upward, you will see positive charges getting deposited at A. Okay? Because positive charges experience force in the direction of V cross B. And you will see negative charges going in the opposite direction. Negative charges will appear at C. So there is a charge separation. So when conductor moves inside a magnetic field, the magnetic field creates a charge separation inside that conductor. Fine. And because there's a charge separation, there will be a potential difference. Now we have to find out the potential difference between A and C. Now this potential difference is what we call as motional EMF. Fine. It is arising due to motion of conductor inside the magnetic field. Okay. Now if you want the potential difference between these 2 points A and C, you have to take the length vector between those 2 points A and C. Do this, all of you. Radiuses are, in terms of radius, you express this length, and then you find out the potential difference between A and C. Try. Any answer?
Sir, L will be 2R, right?
L will be 2R, correct.
And then the formula is VVL.
The formula is B V perpendicular, L perpendicular, correct. Magnetic
So
field
will
is in
it
which?
be
Go ahead. Tell me.
will it be BV2R or something like that?
Okay. Why is there a doubt? See, you have to take magnetic field and then velocity in perpendicular to magnetic field and then length perpendicular to both velocity and magnetic field. I'm telling this to all of you. Magnetic field here is into your screen, means it's in the Z direction. Okay. Velocity is to the right, means it's in the X direction. Is X perpendicular to Z or not? It is. So the velocity V itself is perpendicular to magnetic field. So you can take it as it is. Then the length between A and C, if you connect A and C with a straight line, you see that straight line is in the Y direction. Is Y direction perpendicular to Z and X or not? It is. So it so happens that all three, the magnetic field, the velocity vector, and the length vector, are already mutually perpendicular. So you can directly use them in the formula B, V, L perpendicular is 2R. So that is the potential difference between A and C. Okay. So actually what happens, no? You consider this ring. Imagine it like this. Positive charges have gotten deposited here. Negative charges have gotten deposited here. So effectively, from this positive to this negative, there will be an EMF. Positive side will behave as positive terminal, negative side will behave as negative terminal. And that potential difference is BV into 2R. Similarly, on the other side also. Okay, along that ring, there will be a potential difference developed. And that potential difference, that side potential difference also is BV into 2R only. Okay. In the entire ring, if you see from here to here, potential is increasing, but from here to here, potential is decreasing. So for the total ring, the induced EMF is 0. But between these 2 points, there is an induced EMF. So it's like there are 2 batteries of EMF BV into 2R. The 2 batteries are opposing each other. One is trying to drive current this way. The other is trying to drive current this way. They are opposing each other. That's why the net EMF in this loop is 0. Okay. So that's the potential difference between A and C we have calculated. Next question. Potential difference between B and D. Okay. Between whichever points you want the potential difference, imagine a straight line connecting those points first. Now tell me, how much is this length from B to D?
2R, sir.
This is also 2R itself. Okay. Then tell me the potential difference between B and D.
Sir, in this situation, how do we find out where the positive and negative will be?
Positive and negative are where they are. Positive goes here and negative goes here. You can't change that. Okay. Positive will experience a force in the direction of V cross B. So in this case, positive goes up. Negative will experience a force opposite to V cross B. In this case, negative goes down. You can't change that. Based on that, you tell me what will be the potential difference between B and D.
Oh.
Use the formula, all of you. The formula is B, V perpendicular, L perpendicular. Use that and try to derive the potential difference. Okay. Any answer? See, the magnetic field is B itself. The speed with which the object is moving is V itself, and they are already perpendicular. Magnetic field is in Z direction, velocity is in X direction. Now the length of the line connecting B and D, that is in which direction? The line connecting B and D is in which direction?
It's in the direction of the
The
way it's moving. The
velocity. It's in the same direction as velocity. Correct. It's in the X direction. Okay. Tell me, does that length or the vector drawn from B to D, does it have any Y component?
no, sir.
It does not. Okay. That means in this case, the perpendicular length is 0. The length perpendicular to magnetic field and velocity is 0 in this case. There is no length in that direction between B and D. Therefore, the potential difference between B and D becomes 0. Points B and D are at the same potential. Okay. In this case, charge separation occurs this way. Along the Y direction, there is separation of charge. Positives are going like that. Negatives are coming like this. So along the X direction, there won't be any potential difference. Okay. Positive charges are at A, negative charges are at C. So electric field will be from A to C in the Y direction. There won't be an electric field in the X direction. Okay. So between B and D, the potential difference in this case is 0. Next, between A and D, do this all of you. I want all of you to answer this. You imagine the line connecting A and D. Find out how much that length is. Find out how much the perpendicular component is. Use the formula B, V perpendicular, L perpendicular, and tell me an answer. Do this all of you. Type your answers in chat. Any answer? Okay. Rishi, unmute yourself. We'll discuss.
Yes, sir.
Ha. What are you asked to calculate?
The potential difference between A and D.
The potential difference arises because a conductor is moving in a magnetic field. So we are talking about motional EMF. What is the formula for motional EMF between 2 points?
BVL.
Tell the formula properly. It's not always BVL. It's B, V perpendicular, L perpendicular. Okay, always remember it this way.
Oh, okay, sir.
Because if you remember it as BVL in the exam, like imagine yourself sitting in the final exam, in a hurry, you will directly take the total length. Total length does not always matter. Okay. So B, V perpendicular, L perpendicular is what you should be considering. Take the magnetic field B as it is. I'm writing it here. Is the velocity of this system already perpendicular to the magnetic field or not?
It's not, sir.
In which direction is the velocity of this ring?
It's towards the x-axis.
In which direction is the magnetic field?
Z-axis.
Are they already perpendicular or not?
Those both are perpendicular.
Since the velocity is already perpendicular to magnetic field, you don't have to take components again. You can take the velocity as it is. So B and V taken as it is. Okay. Magnetic field was in which direction?
Z.
Z. Velocity is in which direction?
X.
Z and X are gone. Which is the direction perpendicular to both Z and X?
Y.
Y. Okay. So we now have to take the length in the Y direction. Okay. What is the actual length between A and D? And anyway, actual length does not even matter here. A is at this level, D is at this level. What is the length between them in the Y direction? How much is this?
R.
Radius, correct. So the actual length between A and D is that red vector that I have drawn. It doesn't even matter. All that matters is the length in the Y direction, which is R. So the answer is BVR.
Sir, I have one question though.
Tell me.
Did they mention in the question that B and D are like on the radius? Because that's when we assume that the length between A and D is R, right?
B and D are diametrically opposite points. Okay, they're on the diameter.
Oh, okay, sir.
Okay.
I didn't.
Okay.
Yes, sir. Understood.
Okay. Fine. So the perpendicular distance in this case is the distance in the Y direction. So between A and D, the distance in the Y direction is the radius itself. So the potential difference between A and D becomes BVR. Hope this is clear to all of you. If you have any doubts, you can ask. Pradyun, did you understand? Okay. Okay.
Sir, 1 second. Can you go to the last question? I just wanna, Yeah, sir. You can scroll down.
Next case. Again. Okay, for a change, let's assume there's a magnetic field directed outwards. Magnetic field is B, uniform. And assume there is a rod, conducting rod, obviously, rotating inside this magnetic field. Assume this is the pivot. The rod is rotating like this with an angular velocity omega. Length of the rod is L. Okay, in this magnetic field, it is rotating. Okay, so this is also a case of a conductor moving in a magnetic field. So there is a chance that EMF is induced. There is a chance that there is a charge separation and EMF gets induced. Okay. Can you all tell me if there will be a separation of charge in this rod or not? If yes, which side will the positive charges take and which side will the negative charges take? The rod is rotating like this, as like the hand of a clock. Okay. This is going anti-clockwise. So will there be separation of charge? If yes, to which side does the positive charge go and to which side does the negative charge go? That's my question. Visualize carefully and tell. Yeah, what do you all think? Will there be a charge separation in this rod or not?
Yes, sir, there will be.
Okay, which way? I mean, to which side do the positive charges go?
Sir, so the current is flowing towards the right.
Where did current come from?
No, like, 1 second, sir.
Okay. Others, any answer? Will there be charge separation in this case or not? Okay, we'll come back to this. Let us put it aside. Imagine there is a rod moving in the upward direction. Okay, forget rotation. Let's say it is in pure translation only. It's moving this way. Will there be EMF induced in this rod or not?
No, sir.
Okay, Rishi is saying no. Why? Conductor is moving in magnetic field. Why will there not be EMF induced? Is there no space for charge separation?
Oh, it's moving, then yeah, then yeah. it will.
Okay, tell me. Listen, all of you. We determine whether there will be charge separation or not depending on the forces acting on the charge. Positive charges experience force in the direction of V cross B. Negative charges experience force in a direction opposite to it. So first of all, any of you tell me, what is the direction of V cross B in this case? Velocity is in the y direction upward. Magnetic field is out of your screen. So what is the direction of V cross B?
Sir, can you repeat your question?
What is the direction of V cross B?
Rightwards.
It is to the right. You have to place your right hand fingers along the velocity and curl them in the direction of magnetic field. Magnetic field is into out of the screen. For me, this is out of the screen. So V cross B points to my right. Okay, for you all also it will be to your right. If V cross B is to the right, it means positive charges get deposited here and negative charges get deposited here. Positives go in the direction of V cross B, negatives go opposite to the direction of V cross B. There will be motional EMF in this rod. There's a charge separation, there is space for charge separation in that direction, there will be motional EMF. Okay. Now let us come back to the original question that was asked, the rotating rod case. When a rod rotates anti-clockwise like this, you consider any point of the rod or any one particle of the rod, they'll all be moving this way. Okay, for this particle, the velocity will be like this. For this particle, the velocity will be like this. The farther you go from the axis of rotation, greater the velocity of the particle. Why? circular motion concepts, V is equal to R omega. They all rotate at the same rate, but whichever is at a greater distance R will have a greater speed, V is equal to R omega. Okay, so as you move away from the axis of rotation, the velocities of the points will become greater and greater. This time the entire rod is not moving with the same velocity. All the cases we have taken till now, the entire system was moving with a velocity v. Yesterday, last class, whatever we discussed, and even in today's class, whatever we discussed. Okay, but now we are looking at a system where different points are moving with different velocities. But luckily, all the velocities are in the same direction, which is the y direction now. Okay, now all velocities are in the y direction. Magnetic field given in the question is in the z direction. Out of your screen means positive z. Velocity in y direction, magnetic field in z direction, length is in x direction. All three are mutually perpendicular. There will be EMF induced. Okay. We now have to derive how much EMF is induced. Okay, since the velocities are all upwards, V cross B will be to the right again. So positive charges will settle here. Negative charges will settle at the point where the rod is hinged or pivoted. So there will be a potential difference. That potential difference is what we need to derive. Had all points moved with the same velocity, we could have used BVL or BV perpendicular, L perpendicular. Okay, this is applicable when the entire rod moves with the same velocity V. But now, since the rod is rotating, different points will be moving with different speeds. Points closer to the axis move with a smaller speed. Points farther from the axis move with greater speed. Okay, so can any of you give me an idea to derive the total potential difference between the ends of the rods? Between the ends of the rod. The problem is that different points of the rod are moving with different velocities. Okay. In such cases, what we do is we consider a small portion of this rod. In that small portion, between the left end and the right end, there will be a small potential difference. We will derive that and we'll integrate that to get the total potential difference. Because the problem here is that different elements of the rod move with different velocities. So we'll take one element, we'll find out the potential difference for that one element, and we'll integrate that. You'll get the potential difference for the entire rod. Okay, this one element, let's say it is at a distance x from the axis of rotation. If the distance is x, then that element goes in a circle of radius x. If the element is going in a circle of radius x, that means its speed in this direction will be v is equal to x omega. Circular motion concepts. When a particle moves with an angular velocity omega in a circle of radius r, then its speed is r omega. Here, that element which we have highlighted is moving in a radius x. So its speed becomes v is equal to x omega. So we know the speed with which the element is moving. Our aim is to derive the potential difference in the element across the element. For that, we need magnetic field, we need perpendicular velocity, and we need perpendicular length also. Okay, magnetic field is in the z direction. This velocity is in the y direction. So it's already perpendicular, let it be. We need length in the x direction. So we need to take this length of that element. Length of the element can be called as dx. Small change in the x coordinate. So magnetic field here is B. We'll keep it as it is. Velocity of the element is x omega. We'll have to write it as it is. Length of the element is dx. So that will be the potential difference across that one element. If you want potential difference across the entire rod, you'll have to integrate potential difference of all the elements. That means you'll have to integrate b omega x dx from x is equal to 0 to x is equal to L, so that you consider the entire rod. Now B is the uniform magnetic field, so it can be kept outside the integral. The entire rod rotates at the same angular velocity omega. It can be kept outside the integral. You will be left with integral x dx from 0 to L. Can one of you quickly tell me integral x dx? X square by 2. Okay. Therefore, the total potential difference becomes b omega. Integral is x square by 2 from 0 to L. The answer becomes b omega L square by 2. That's the potential difference across the ends of the rod. Okay. So the problem here was that different parts of the rod move with different velocities. So we have to find out small potential difference across one element. We have to go element by element here. We can't use a single velocity for the entire rod. So we took one element. We wrote an expression for its velocity in terms of the distance. V is equal to x omega. And with the velocity, we found out the potential difference in that one element. You integrate it, you'll get the potential difference in the entire rod. Hope the idea and the procedure is clear to all of you. If you have any doubts, you can ask, otherwise note it down. Okay. Fine. So listen, what we discussed last class and this class is one of the ways in which EMF gets induced when flux through a coil changes. Okay. Magnetic flux is B dot A, that is BA cos theta. So to change flux, there are many ways. You can change the magnetic field, you can change the area, you can change the orientation. Okay. So what we have discussed is when area or orientation changes, why EMF has to get induced. That is what we have seen till now. Because when area is changing or orientation is changing, conductor will move. So motional EMF will get induced. That's what we have discussed till now. But there is another way to change flux. You can change flux simply by changing the strength of the magnetic field. Don't do anything to the loop. Okay, you don't have to increase the area of the loop. You don't have to rotate the loop. Don't do anything. Just change the magnetic field. That induces EMF. In fact, that is what Faraday observed. We discussed the first observation that Faraday did. Okay, Faraday kept the coil there itself. He brought the magnet close to it and he found that there was current flowing in the coil. Basically, what happens when you bring magnet close to it? Field becomes stronger. Area of the coil is not changing. Orientation of the coil is not changing. But the field passing through it is becoming stronger. Flux is changing. Okay. So simply by changing a magnetic field, it is possible to induce EMF. Right? How? How does EMF get produced when a magnetic field changes? When area or orientation changes, conductor moves. So positive charges will go to one side, negative charges will go to the other side. That mechanism we know. If magnetic field changes also, there will be an EMF induced. Now, this is through something called an induced electric field. Okay, listen carefully, all of you. Induced electric field. Basically, suppose there is some space, let's say there is a region in which there is some magnetic field present. If you change that magnetic field, no, automatically it produces an electric field. That's all. Okay. And that electric field is what we call as induced electric field. This is not produced by charges. This is not produced by charges. Usually what we learned about electric field is that field lines emerge from positive charges, they terminate at negative charges. Charges produce fields, electric fields. Okay. But there is another way to produce electric field also without charge. So when magnetic field in a certain region changes, what do we mean by magnetic field changing? Its strength could change, its direction could change, whatever it is. If magnetic field in a certain region changes, it automatically produces an electric field. Okay, this electric field is what we call as induced electric field. So this is not the regular electric field, not like the regular electric field that we studied till now. Okay, this electric field arises from a time varying magnetic field. Okay, let us discuss this in a little detail. Consider a loop like this. Let's say this is a conducting ring. Listen very carefully, all of you. I'm assuming there's a conducting ring present. And assume there is a magnetic field directed into the plane of the screen. If there is field directed into the plane of the screen, it means there is flux through this ring. Some field lines will pass through that ring also. Okay. Let's say this magnetic field is becoming stronger. Means its strength is increasing. Now you all tell me, if the field strength increases, will the flux through the ring change or not?
It will, sir.
It will. Is the flux becoming stronger or weaker?
It will become stronger.
Obviously, field strength is increasing, so flux becomes stronger. Correct. Field lines are directed into the screen and the flux is becoming stronger. According to Lenz's law, what should the induced EMF do and how will current flow in this ring? All of you think and answer. I want answers from all of you. Lenz's law, you all were present. What is the direction of induced current in this ring? That's my question. I got one answer as anti-clockwise. Others also. What do you think is the direction of induced current in this ring?
Sir, since it'll be opposing the induced electric current, it'll be anti-clockwise.
Okay. Okay. See, the magnetic field is into the screen and it is becoming stronger. So flux, inward flux is increasing. Induced EMF will always drive current in such a way that it opposes the change in flux. Inward flux is increasing, means we have to somehow decrease it. So the induced EMF will produce an outward flux. The induced EMF has to drive current in such a way that magnetic field gets produced out of your screen. To produce a magnetic field out of your screen, the current will have to flow anti-clockwise. So in this ring, the current flows this way, anti-clockwise. Now listen, all of you. For current to flow anti-clockwise, there must be an electric field generated. Electric field is what makes current flow in a conductor, right? Potential difference means electric field only. So basically, this magnetic field that is there, whose strength is increasing, is producing an electric field. That is how it is able to drive that current. Because this is not motional EMF. The conducting ring is not moving inside the magnetic field. Okay. So this is not motional EMF. Then what makes the charges move in this case? What makes current flow in this case? There must have been an electric field generated somehow. And who is there, or what are we doing to generate the electric field? The only thing we are doing is changing the magnetic field. Then that must have been giving rise to an electric field. Okay. And since current is flowing anti-clockwise, we can conclude that there is an electric field produced somewhat like this. Anti-clockwise. Okay. And in fact, even if the ring had not been there, this electric field would have been produced by the magnetic field. Okay, it was observed scientifically, experimentally, they have checked it. If ring is there, current will flow. If ring is not there, like what is making that current flow? This electric field only. If ring is not there, current won't be there, but the electric field will still be produced. Okay, this electric field is what we call as induced electric field. Who is producing this electric field? The magnetic field is producing it. The time varying magnetic field is producing it. So whether the conducting ring is present or not, whether or even if an insulator is present, it doesn't care. If magnetic field in a particular region varies, it will automatically generate an electric field. If you put a conductor there, that electric field will make charges flow. It will make current flow. If conductor is not there, current won't flow, that's all. But field will be there. So this is what we call as induced electric field. What's the difference between induced electric field and the usual electric fields that we used to talk about? The usual electric fields that we used to talk about were generated by charges. But induced electric field is not produced by charges. It is produced by a time varying magnetic field. This one. Okay, that is one difference. Another difference, one of you tell me, do electric field lines form closed loops?
No.
No. The regular electric field lines, they originate from positive charge and they get terminated at negative charge. They don't form closed loops. But induced electric field lines always form closed loops. That way it's different from the normal electric field. Okay, so here actually, if you visualize the field line, it will be like this. Induced electric field lines, just a moment, they form closed loops. There's no point of origin or termination. They form closed loops. Yeah, what do you want to ask?
Sir, will this always be the case?
Will what always be the case?
Like closed loops when there's an induced electric field.
Induced electric field always forms closed loops, yes. Okay, and observe one more thing also. Here, what is the direction of the magnetic field? In which direction is the magnetic field in this case? Look at those crosses and tell me what is the direction of magnetic field that we have considered? Inwards, Z direction. Okay, and that field is varying in strength. So magnetic field is varying in the Z direction. In which plane is that induced electric field? Magnetic field is in the Z direction. Induced electric field is in which plane?
XY plane.
XY plane, correct. This is also always true. In whichever direction you have the magnetic field, the induced electric field gets produced in a plane perpendicular to the direction of magnetic field. So here magnetic field was in the Z direction, induced electric field is in the XY plane. Had the magnetic field been along the x-axis, induced electric field would have been in the YZ plane. It always happens like that. Okay. So let me write the properties here. First, induced electric field is produced by time varying magnetic fields. So I'm writing it as B of t, magnetic field which changes with time. Next, induced electric field lines always form closed loops. Next, induced electric field is always in a plane perpendicular to the magnetic field. So if magnetic field is in Z direction, as we have seen in this example, induced electric field lines will be in the XY plane. Okay. And whether that induced electric field will form clockwise loops or anti-clockwise loops, that you can tell from Lenz's law. Here, in the example that we have taken, inward magnetic field is becoming stronger. So induced current should flow anti-clockwise and produce an outward magnetic field. For induced current to flow anti-clockwise, there should be an induced electric field in the anti-clockwise sense. That way we can tell the sense of the induced electric field. Is this clear to all of you? This is another reason why EMF gets induced in loops when magnetic flux changes. There are many ways to change flux, right? You can change field strength, you can change area, you can change orientation, you can do one or more of these. So when you change the area or the orientation, what gives rise to EMF is motional EMF. The motion of a conductor in the magnetic field causes charge separation, so you will get motional EMF. But without moving the conductor also, without moving the loop also, if you simply change magnetic field, you will get EMF. How is that happening? Through induced electric field. Okay, so it has been found and verified that a time varying magnetic field produces an electric field automatically. So if there is a conductor here, that electric field will drive the electrons in that conductor and it will make current flow. But if that conductor is not there, also electric field will be produced anyway. Fine. So let's answer some questions based on this, all of you. First, tell me, what produces an induced electric field?
Sir, a time varying magnetic field.
Time varying magnetic field. So if there is a field and it gets stronger or weaker, if there is no field and you suddenly switch on a field, that is also a time varying field only. From zero, it becomes non-zero. Okay, in all those cases, induced electric field gets produced. Okay. So think about this, all of you. Suppose there's an electron. Negatively charged particle, need not say that. Assume it's at rest. Okay. See, practically it's impossible to keep an electron at rest. But let's assume, hypothetically, let the electron be at rest. Initially, there's no magnetic field. Now, the question is, if we switch on a magnetic field directed into the plane of your screen, What happens to the electron? Will it move or will it continue to be at rest? If it moves, can you predict the direction in which it moves? If you cannot predict the direction, that's fine. You can tell that. But think about it first. Any answer? What do you think will happen? Will the electron move or not?
Sir, I think it'll move.
What makes it move?
Sir, the induced electric field.
Induced electric field, correct. See, if we switch on a magnetic field, that means a zero magnetic field is becoming non-zero. Means we are changing the magnetic field that will produce an electric field. And if there's an electric field, it will exert a force on the electron will start moving. Okay, listen all of you. The magnetic field is switched on into the screen. Means flux into the screen is increasing. There was no flux into the screen initially, but when you switch on the magnetic field, it generates an inward flux. Means from zero, it is becoming non-zero into the screen. Then induced current should create an outward magnetic field. So there will be an electric field, induced electric field generated like this. Had there been a conductor, current would have flown anti-clockwise. Means the electric field generated is anti-clockwise. Now you don't know where exactly the electron is placed. Now electric field lines, induced electric field lines form closed loops. So let's consider one closed loop. Assume it's a circular loop itself. Okay, let's say this is the electric field line, induced electric field line. Now, if the electric field line gets generated like this, fine, electron experiences force opposite to electric field. Okay, at the position of this electron, the electric field is in this direction. Then force opposite to it would be this way. So electron will experience force in that direction. That possibility is there. But suppose the induced electric field, the electric field line is like this. We don't know where exactly the magnetic field is switched on and all. No? So suppose the electric field line, induced electric field line is like this. That means at this point where the electron is present, the electric field is in this direction. Electron experiences a force opposite to electric field. Then the force will be this way. So we can't exactly tell which way the electron is going to experience a force. Okay, it depends on the exact space in which you are switching on the magnetic field. That will decide the exact direction of electric field, and that will decide the exact direction of the force on the electron. So that we cannot tell, but it will experience a force, that much we can tell. Why? Because we suddenly switch on a magnetic field. It means we are changing the magnetic flux. So automatically an induced electric field will get produced, and that will exert a force on the electron. Okay. Next class we'll discuss in further detail about this induced electric field. Actually, they won't ask you many questions based on it because there's only one formula that you can derive for. There's no fixed formula for induced electric field. In one case, using some logic symmetry, we can derive how much electric field will be produced. But there's no general formula for induced electric field, so they won't ask you many questions based on it. So you need to remember that if magnetic field changes, okay, in a certain region, automatically electric field will get produced in that region. That electric field is called induced electric field. Okay, we'll stop it here for today.